thank you TSDCA for hosting today's second session. Last week we spoke about SpaceMap Go introduction by Josh Dorn-Furman, and today will be about MAPP 3D. My name is Merlijn van Veen. I'm Senior Technical Support and Education Specialist at Meyer Sound, and today I am joined by co-host Josh Dorn-Furman, who is also Senior Technical Support Specialist.
Greetings from Champaign-Urbana. Hello, everyone. I'm actually in a theater doing a constellation system right now at Krannert Center for the Performing Arts. So it's a good day.
We'll try to keep it under an hour, but basically what we're intending to do during today's session is give you the highlights of what is actually 4 roundtables that last 1 hour each. So we had to apply a 4:1 compression ratio. We singled out some of the topics that we feel are most important to start off with, and those we will discuss today. So we're going to start with giving you a background information on MAPP, which stands for Multi-Purpose Acoustical Prediction Program. We're going to look at a brief overview of the graphical user interface in MAPP 3D so that we feel comfortable with navigating the software. We're going to talk about viewports, how to import CAD or SketchUp drawings, including DXF files, how to add geometry using the built-in tools that allow you to draw 2D shapes and 3D solids, or even free draw shapes with or without help of a snapping tool. Some of the modifiers that allow us to perform operations on those pieces of geometry, such as the trim modifier, but also extrusion. We can do linear extrusion, we can do angular extrusion, as we're about to discover. Some of the other primitives, as I already said, include 2D shapes and 3D solids. Also, the 3D solids we can massage using certain Boolean modifiers that we'll talk about. A technique that we've lovingly come to call the cookie cutter approach, which is very expedient. We'll look at that as well, time permitting. We'll talk a little bit about how SPL is rendered in the model view. We're going to limit today's session to looking at attenuation only. We'll leave SPL for another day. And then some tips regarding performance, calculation speed, and workflow. We'll like to manage some expectations regarding that. And finally, how to integrate with the mature Compass control software, as well as Compass Go, which is the iPad app, how to integrate and have those speak to each other. Finally, where to download the application, where to find additional help, and what to do if you have feature requests or feel that a certain loudspeaker model should be added to the inventory, how to address that, and then hopefully there will be some time for Q&A in the end. So as promised, let's start with some background information regarding MAPP. The development of MAPP basically began when John Meyer decided to build the anechoic chamber in the Bay Area in 1995. Now, what we see here is a vintage piece of computer-generated imagery, CGI. We're about to enter the anechoic chamber. Camera is about to swivel around, and we see the door close behind us. And in the middle of the room, there is a contraption which we come to call the positioner. And it's the positioner that allows us to pivot and rotate the loudspeaker with respect to a stationary microphone. And that's how we capture the polar information of the loudspeaker at high resolution, as we're about to learn. All of that goes back to 1995, the building of the anechoic chamber. And this is also with all the data that was coming out of this anechoic chamber. All that data needed to be visualized one way or another. And that basically constitutes the inception of MAPP. Now here we see a close-up photo of the positioner. It houses a loudspeaker, which we call the device under test, and the arm has two servo motors. There's one servo motor at the base, and there's one servo motor behind the U bracket that contains the device under test, and that allows us to pivot and rotate, or I should roll the loudspeaker, and pivot the loudspeaker, and that's how we get our measurements. The microphone in the chamber is roughly at 4 meters distance, and it's stationary. So rather than using the microphone to orbit the loudspeaker, it's the microphone that is stationary, and it's the loudspeaker that is being rolled and pivoted. And that means that in the era before MAPP 3D, MAPP XT, as you're well aware, used to be 2D, but within the constraints of a two-dimensional plane, we would capture at 1 degree angular resolution 360-degree measurements per loudspeaker in one dimension, and of course also 360 measurement points per loudspeaker in the vertical plane. And all of those measurements were high resolution, that's to say 48 points per octave, containing both magnitude as well as phase information, for which you can then extract the impulse response as well by means of a process known as inverse fast Fourier transform. Now, 48 points per octave, just to give you an impression, if you look at a vanilla graphic equalizer, then there are 3 faders between 1 kilohertz and 2 kilohertz. So when we talk about 48 points per octave, we're talking about 48 faders between 1 kilohertz and 2 kilohertz. Suffices to say that is high resolution data. And that led to the inception of MAPP, which at the time was called Meyer Polar 2D. And it was in grayscale colors. But what it allowed you to do at the time in 96 is that at the cursor readout, where we see the crosshairs, it would show in real time the frequency response. And since we're dealing with 2 sources that are separated by a physical distance, you get an interference pattern showing power alleys and power valleys and power alleys and power valleys. And if you look at one point in space, for those that are in the know, that results in a comb filter. But it would do this in real time. Wherever you put the crosshairs, you would see the frequency response. And that basically was the primordial version of what later became MAPP. The first commercial available version or freely available version of MAPP used to be MAPP Online, which was launched 2 years later in 98. And it set the bar for trusted data, high resolution data, accurate data, and it basically caused a landslide, especially in the field of subwoofer arrays, where we try to achieve control by committee by clever arraying the subwoofers in an attempt to steer the sound where it needs to go, which is to the audience and not towards the plaster. And suddenly we could see that in a two-dimensional plane for every position in that plane, which is typically the listening plane. Because of the huge calculations that are involved with doing these highly accurate measurements and creating these highly accurate predictions, that took place by means of a patented client-server method. So basically, MAPP is a piece of software that runs on the client computer, and it then speaks to the servers in the Bay Area, and the servers send back the actual prediction data. With MAPP 3D, you no longer need to be online, and that's of course a huge advantage. We've spent decades at proving the accuracy of MAPP. White papers have been written, papers have been published, all to underscore empirically that MAPP is above all is accurate, and MAPP 3D continues to sustain that legacy. MAPP 3D, by all means and then some, continues to be just as accurate as MAPP XT and MAPP Online before that. And that's something that is very dear to us. That being said, we've never stopped paying attention to 3D predictions of sound propagating through a room. Already in 2001, Per and Meyer was looking into ways to predict the 3D propagation, three-dimensional propagation of sound in a room. And here we see some research that dates back to that period showing ISO pressure balloons. And that means that if you were to navigate or walk the surface of the balloons that you see over there, you would perceive the same pressure, i.e. the same level wherever you wander over that balloon shape, never mind how peculiar it looks at certain points. But again, that is a big testimony to accuracy. All those little high granular extrusions you see, that is a testimony to the frequency resolution and accuracy that we continue. It's the pinnacle of what we're trying to do, that we continue to sustain in all these programs. So the development of MAPP 3D began in 2015, and in order to do so in an expedient way, we also had to develop new ways to measure our loudspeakers, starting with the microphone array that you see to the right. So we no longer have a single microphone with a loudspeaker that is orbiting and pivoting, we now have an array of microphone which contains 10 microphones rather than one, and that speeds up the process of scanning by a factor of 10, because every time we rotate the loudspeaker, we get 10 pieces of information rather than one piece of information. And internally, MAPP3D has been using by our design services team ever since early 2019. Those multi-channel polar scans are made of each reference loudspeaker just for continuity. So of every loudspeaker in our portfolio that's out there, there is the mold, if you will. There is the master loudspeaker, the template that is carefully kept in our warehouses. And we always keep going back to those loudspeakers for continuity reasons, because we want MAPP3D to replicate exactly the same results as we expected to see in MAPP-XT and MAPP Online before that. So great effort is put into continuing that that performance, that accuracy, that precision. And that means that the raw data at first for a single loudspeaker, which we lovingly call a POL file, exceeds 80 gigabyte and requires about 8-hour automated process together. But then after post-processing, because there's redundancies and whatnot, each resulting POL file is about 135 megabytes. And one of the first things that you'll end up doing when you start using MAPP3D is to download the relevant POL files to you of the loudspeaker models that you use in your daily activities. That's one of the first things that you end up doing, which is download those POL files. And a finished POL file, just to give you a crude impression, a finished POL file, again, has the 1 degree angular resolution that we already saw in the world before MAPP3D, which was 2-dimensional, but it continues to use the 1 degree angular resolution. And that means that when you do this over an entire sphere, you're looking at over 65,000 measurement points. And just for measure, the graphic to the right shows less than 2,000 points. So it's incredibly high resolution, and that allows us to continue that legacy of being known to be accurate and precise. And at each point, we continue to capture those 48 faders between 1 and 2 kilohertz, the 48 points per octave frequency resolution. So that is a little bit of background information regarding the development and evolution of MAPP3D. And with that, I would like to move on to giving you an overview of the graphical user interface. So for those that are not familiar with MAPP3D, if you open up the application, it defaults to this layout. And basically, there are 4 major areas. There's the center pane, which obviously lives in the center. Then there is a pane to the left, there's a pane to the right, and there's a strip in the top. And we're going to look at those sections one at a time. So in the left pane, we find our geometry, our signal processing, our loudspeaker systems, as well as our microphones. So basically it's our inventory, your spheres, your 2D shapes, your listening planes, your galaxy devices, your loudspeakers, arrays, point sources, and whatnot, and multiple microphones that you can drop into the listening plane to see the same data one has come to expect of MAPP-XT. We show the phase response and the magnitude response and the impulse response and the A and the C and the Z weighted values. All of that information is readily available. Whereas if we move to the right pane, starting in the top right corner, we have our tools where we can use select and orbit and measure the distance using a ruler. We can scale, rotate, array, mirror, zoom in, zoom out, zoom to extend, and array geometry, as well as loudspeakers in rectangular arrays as well as polar arrays. Below that, we have our primitives, which consist of 2-dimensional shapes and 3-dimensional solids, including a pencil that allows you to draw shapes of your own choosing. And this is also where we find the modifiers. And the modifiers allow us to perform a bunch of operations on our geometry to come up with very interesting and complex shapes in a matter of minutes. And then this is also where we find some of the properties of whatever object we're working with. So it could show the properties of a piece of geometry, but it could also show the properties of an audience plane and whatnot. And this is also where we have a second top, which houses the layers. Now, these are layers as you've come to expect from computer-aided drawing software such as SketchUp, Vectorworks, or AutoCAD. And this is also the functionality that we had in MAPP-XT, which is allowing you to organize your objects, microphone, loudspeakers, visual architectural aids at the time. You can organize those in layers, lock them, hide them, reveal them, give them a color of your choosing, and basically structure your workflow. And then finally, in the bottom right corner, we also control our viewports. We can work in a single viewport, and we can work in multiple viewports and even create our own camera angles. Now, when we get to the center pane, that defaults to 1 out of 4 tops, which is the model view. And the model view is literally what it says. It's where we view our model. Over here, we see a rather familiar spacecraft. But if we go to the second top, it also shows us the settings of our object, which in this case happens to be a beam or a cube or whatever you want to call it, a rectangular shape. And it shows how many faces it has. It shows width, length, and height, and all of those obvious parameters. But this could also show you the properties of a loudspeaker, such as the Ultra X40 in this case, where we see its 3D coordinates in space, X, Y, and Z, and how it's rotated and panned and tilted and rolled, to what galaxy it is assigned and to which output channel it might be assigned and how much power it consumes, and the weight. All of that is shown in that object settings top for a single loudspeaker, but also for arrays and whatnot. Whereas if we go to the third top, we have our processor settings, and that features everything that you have come to expect to find in Compass or Compass Go for that matter. Basically all the signal processing available on our Galileo Galaxy devices, such as EQ, even delay integration that allows us to make our loudspeakers phase compliant, polarity reversals, delay, output gain. You can mute loudspeaker channel, or you can mute processing channels, if you will. This is also where you do your low mid beam control and whatnot. So all the bells and whistles you've come to expect can be found there as well. And then finally, the measurement view, or what we lovingly call virtual sim, showing you your magnitude response for a microphone somewhere within your model, as well as its phase response, the IFFT, which we colloquially call impulse response. All of that is shown. We can store those traces and give them offsets like you would do in Smart, and recall those traces for comparative purposes and whatnot. Set a delay locator. And this is also where we find our headroom plot that you've come to expect from MAPP, showing you your A, C, and Z weighted average sound levels, as well as your peak sound levels, all of that information for that microphone at a particular point in space. And then finally, that top pane, that is where we control our signal generator. Are we using pink noise? Are we using B noise? Or are we using M noise? And what is the generator level? All of that is controlled in the top left corner. Next to it, we have our prediction controls, where we allowed to choose can choose the bandwidth that we want to predict. Do you want to predict 1 octave, a third of an octave, a sixth of an octave, centered at which frequency, at 4 kilohertz, 2 kilohertz, 1 kilohertz, so on and so forth. And that's where we start the prediction, start the number crunching by hitting the predict button. Then there is a little section that basically shows you the extreme SPL values. It will show you the maximum SPL value within your model, and will show you the minimum SPL value within your model, just as a friendly reminder. And then also some power consumption metrics, including the current that is drawn by your Galileo Galaxy devices, or Callistos or Galileos before them. All of that showing in the top right corner. And with that, I want to move toward the topic of viewports. So here again, we see a single viewport. We're looking at viewport number 1, showing a rather familiar spacecraft, but we don't have to work with a single viewport. We can also click multiple, in which case we're going to get multiple viewports, and we can choose the camera angle of any viewport by using the drop-down menu in the top left corner, which has several camera angles already pre-populated, but we can also create our own camera angle and store that with its own dedicated name, so that we don't have to massage the camera each time we want to revisit that particular angle. We can do that for a single viewport, and we can do that for multiple viewports at once. And I think this gives you a rough overview of the graphical user interface, and should get us to a point where we maybe can start adding some geometry, and why not start with importing some CAD drawings and possibly SketchUp drawings first. So over here we have a grid. That grid is showing us our two-dimensional plane. It has a red x-axis, it has a green y-axis, it has a blue z-axis, And the first thing I want to show is how easy it is to import either a SketchUp or a DXF file. So in order to do that, we're going to go to File, and under File, we're going to go to Import. And in Import, there's two file formats to choose from. There is the DXF, which stands for Drawing Exchange Format, which is supported by all major computer-aided drawing software. And then there's SketchUp. I'm going to start with the DXF first. I'm going to open this, and then it brings up a dialog. It needs to know what is the incoming unit. What is the unit that was used in the DXF file? Well, I happen to know that it happens to be inches in this case, but that could be trial and error if you don't know what the incoming unit is. So if I'm going to click inches and I'm now going to click import, then within a matter of seconds, we'll get a dialog informing us that we've successfully imported the DXF file. And there you go. There is our imported DXF file of an outdoor venue with a amphitheater kind of style audience arrangement. It will show up under layers here. Notice that layer 1 with DXF between parentheses, this is now the layer containing my imported DXF. I can hide it, I can reveal it. If the incoming DXF file happens to have additional layers that are nested underneath all those layers, that structure will be preserved, including the colors and whatnot. So if you already did some organization within AutoCAD or Vectorworks, all of that layer structure will be preserved. So let's hide this guy and do it once more, but this time around we're going to import the SketchUp version of the same venue. This time I'm going to take the SketchUp version, I'm going to click open. For those that are not aware, SketchUp is always in inches, no matter what, and that means that the distance unit is set to auto. And if I now click import, we're going to get another confirmation that we've successfully imported this SketchUp file, and lo and behold, there we see exactly the same venue that we saw before. And notice that it shows up in a second layer, and that means that your Map 3D project can house two drawings at once. It can house the DXF and it can house a SketchUp file simultaneously. If I were now to reveal the DXF file once more, you're not going to be able to see a difference because these files are functionally the same venues, but rest assured, there is very much two instances of the same venue. That is how easy the process of importing a DXF or a SketchUp file can be, provided your file complies with certain formatting guidelines. For those that use these kind of programs on a regular basis, you know that there are a lot of entities that you can encounter in computer-aided drawing software such as AutoCAD or Vectorworks. And despite our best efforts, not all of those entities are supported in MAPP 3D. And there's also some good practice in general, which is to eliminate some redundant elements, such as bathroom or toilet stalls, bathrooms, lobby doors, all of that. We don't need those elements in our drawings to find out how we need to aim the loudspeakers. So it is prudent to remove any redundant elements that have no direct implications for how we aim the loudspeakers, how we deploy the loudspeakers. It's also prudent to replace complex elements with simple elements. Over here, we see some chairs, and these chairs are very detailed. They contain a lot of lines and vertices and whatnot. But again, we don't need that granularity to aim our loudspeakers. So it's prudent to replace those rather complicated shapes for shapes which consist of fewer polygons, fewer vertices and whatnot. And in general, it is expedient to keep the file size reasonably low, preferably under 20 megabytes. That being said, larger files are supported. The entities that are guaranteed to work are lines and polylines. So regardless whether you work with AutoCAD or with Vectorworks, if you achieve to export your DXF file in a way that it consists only consists of lines and polylines, the import process, as we just witnessed ourselves, is gonna work effortlessly. How to make that happen, you could dedicate several webinars to that, but that's a little bit out of our mission statement. We're a loudspeaker manufacturer. We do not train people in using AutoCAD or Vectorworks. That being said, we don't want you to feel, we don't want to leave you hanging out dry there. So there's a few ways how you can make sure that your file contains lines and polylines. For those that use AutoCAD on Windows machines, for example, there's a beautiful piece of software. Think of it as a plugin, which is known as Curve Segment by Lee Mack. And what it allows you to do is to choose any of your splines and other entities which are not supported by MAPP 3D and replace them for linear approximations based on the number of segments that you choose that suffice effortlessly for the job description of aiming loudspeakers. Another tried and tested way is to parse your DXF files first through SketchUp Pro and then export those as a SketchUp file because SketchUp is also supported very well in MAPP 3D. I don't want to spend too much time discussing this, but we have an entire webinar dedicated how to curate your files, to tailor them, to make them suitable for import into MAPP-XT. And suffices to say that if you can import them into MAPP-XT, you can also import them into MAPP 3D. And if you still find yourself struggling with making your DXF files or SketchUp files suitable for MAPP 3D, by all means, reach out to Meyer Sound Technical Support. We can typically have those files formatted properly, have them back with you within reasonable time. And with that, I would like to go forward with the remainder half hour or so at looking at how to insert objects. Now, this is what you need to know about MAPP 3D. We can have multiple viewports, each with their own camera angle. So you could have a top view, you could have a left view, and you could have a front view. And whenever you use one of those views, you are orthogonal to the plane that you're observing. So that means that when you observe the XY plane, which is effectively a top view or plan view, and you were to insert a piece of geometry or start drawing using the free draw tool, then it will automatically snap to the XY plane. Whereas if you're doing a left view, which would be a section view, and you're orthogonal to the XZ plane, then any geometry that you add or any loudspeakers or any free drawing that you're doing will automatically snap to the XZ plane and set the Y coordinate to 0. Whereas if you're doing a front view, imagine that you're observing the stage from front of house, then you're observing the YZ plane. And if you now put in a piece of geometry or a loudspeaker, then the X coordinate will default to 0. And to make that a little bit more intuitive, I think this is a nice moment to start doing rather than showing you the abstraction. So Josh, can we see the X-Wing once more?
Yep. And just one thing I put in the chat that everyone should be aware is Vectorworks, since we are working in with TSDCA, and a lot of people use Vectorworks. Vectorworks has a lot of built-in convert to lines and polylines tools that you can do. So you don't need a third-party tool to do that within Vectorworks. So there you go. Back to you, Merlijn.
Thank you, Josh. So here we have an isometric view of the rather familiar spaceship, and I'm going to change from one viewport to multiple viewports. And this clearly shows you that we have a plan view or a top view, we have a section view or a left view, and we have a frontal view. And I'm going to make this a little bit more easy to digest because I'm going to activate two-dimensional planes that I already prepared in this file so that you know at what plane you are watching when I start adding geometry. Now, I'm done with the spacecraft for now, so I'm going to hide the spacecraft, and we're only going to keep the planes so that you know at which plane you're looking. And I'm going to use the free draw tool. And using the free draw tool, I'm going to start by drawing a triangle in plan view. And if I draw a triangle in plan view, and maybe I should choose a different layer for a more distinguishing color. So by triple clicking on the free draw layer, which I already gave a white color, that now becomes the default layer, similar as in AutoCAD. And now I'm going to start drawing a triangle in the top view. And a triangle has 3 points, and this is where you're going to get your first tip. If I want to close this shape, and make it a triangle, all that I have to do at this point is press the C key on my keyboard, the C for close. And that will finish that shape. It will close the shape. And notice that that shape ended up in the yellow plane because I inserted it in plan view. So now we're going to add another shape. Why don't we start drawing a rectangle in the left view? And if I start drawing a rectangle in the left view, notice that it ends up living in the purple plane. I want to finish this shape. I'm going to hit the C for close, and that completes my rectangle. And notice that this snapped to the purple plane. This snapped to the XZ plane. And finally, I'm going to go to my front view, observing the stage from front of house, and I'm going to draw a diamond kind of shape. Come on, you can do it. Let's draw the diamond. And there we go. And again, I'm going to hit the C key for close, and notice that this diamond shape ended up living in the blue plane, the cyan plane, which is my YZ plane. So that is what happens when you add geometry or loudspeakers. They always will snap to the plane that you are orthogonal to. And with that, I want to start doing some additional exercises because we have our primitives, we have our rectangles and ellipses, which can also be a circle, obviously. And let's see how we can manipulate those and get some work done rather quickly. So I already have a project prepared for this, and that is going to be the church example. So imagine the following situation. You have a floor plan, a two-dimensional CAD drawing, and basically using a bunch of rudimentary shapes that are available from the primitives. We have a circle, we have a rectangle, which happens to be the transept, and we have another rectangle, which happens to be the nave. I could easily come up with these shapes just by looking at a plan view of my venue. But now I want this to become a single continuous outline rather than a collection of shapes. In order to turn it into a single outline, we're going to use our first modifier, which is known as the trim modifier. And in order to use the trim modifier, we have to choose two pieces, two-dimensional shapes at once. We can do a drag and drop, or we can just use shift and choose the both pieces of geometry from my inventory. We can use them at the same time. The shapes need to overlap. So while we start with these two rectangles, they're clearly overlapping. I'm now going to choose the trim modifier, and the trim modifier allows me to eliminate the line segments that I have no more interest in. Once I'm done, all that I have to do is hit enter, and what used to be 3 shapes has now been reduced to 2 shapes. Now I'm going to do either left click and drag. I'm going to select my 2 remaining shapes. I'm going to do another iteration of the trim operator. I'm going to cancel this, and I'm going to cancel that line segment. I'm going to hit enter once more, and suddenly, within a matter of seconds, without explanation, I have the outline of my floor plan. And what can we do from here on? Well, we can select that shape once more, and we can use a different modifier, which is known as the extrude modifier, and that basically allows us to turn our 2-dimensional shape into a 3-dimensional solid. So I'm going to extrude along the z-axis by 15 meters or so, and if I now hit apply, lo and behold, there we have a 3-dimensional solid rather than a 2-dimensional shape. And while we're on this topic, if I were to add a loudspeaker and I wanted to make any predictions, then I need to tell Map 3D which planes are nominated to show the propagation of sound. Where do I want to see the propagation of sound? And we can do that for the entire 3-dimensional solid, including the walls and the ceiling, by activating prediction. And that will give the entire shape a purple hue. And that means that if I now were to introduce a loudspeaker, I would see the propagation of SPL on all of these boundaries, including the boundaries where nobody is listening. So I could also choose my geometry and go to its object settings. And in its object settings, I have a list of all the faces that make up for this three-dimensional solid. And notice that when I mouse over any of these faces, that it lights up in the preview upstairs. So all that I have to do is go down my list until I find the floor, and that is probably the plane or one of the planes that I want to activate for predictions. While we're here, notice that we can also give this plane an offset, because after all, our ears are not where our feet touch the floor. Our ears are typically anywhere from 4 feet to 6 feet above that. This is set up to be meters, but if I were to give this a 1.2 meter offset, notice that the listening plane is now hovering 1.2 meters, which is about 4 feet, hovering 4 feet above the actual floor of the three-dimensional solid. So there you already see some of those modifiers come together, and clearly you can see that this works rather intuitively. So let's go to a new project and let's start looking at those other two-dimensional shapes and some of those 3D solids, and how we can use some of those operations to come up with relatively complex shapes within a matter of seconds. So what if I need a sphere? Imagine that you need a sphere. Well, we're going to start with a circle, and we're going to center it in our model view. And let's make it a circle by giving it equal depth and width. And if I wanted to turn this into a sphere, I could use the same extrusion technique. But in order to do that, I wouldn't need to put the circle upright first. So I'm going to rotate it along the x axis. I'm going to roll it, and now my circle is upright. And now I'm going to use a different application of the extrusion tool. This time I'm going to use a angular extrusion of 180 degrees with a pivot point at xy equals 0. And what that will do is we'll do an angular extrusion and effectively turn my circle into a sphere. And again, within a matter of seconds, I have created a rather complex shape, which has several phases that I can activate for prediction. Now, what if I wanted to create a donut? Could I go about it the same way? Sure, let's start with our circle. Once more, let's give it some dimensions, maybe 5 by 5 meters. Let's put the circle upright once more. But this time I'm going to offset it out of the center of my model space, maybe by 5 meters or so. And again, I'm going to go to angular extrusion. This time I'm going to do a 360 degree extrusion, again around the pivot point xy equals 0, 0. And if I now hit apply, lo and behold, rather than having a sphere, we now have a donut. And if I were to activate this for prediction such that it gets a U that we can actually see, now you see that over here we have a donut. So with a little bit of imagination, you can start to appreciate that you can come up with rather complex shapes using these techniques. Let's do one more. If I want to do a hemisphere, I have to combine several techniques. So let's do another circle. Let's keep it 10 by 10, whether these are feet or meter. And I first gonna change this into a hemisphere rather than a circle. So I'm gonna draw a line, and that line will consist of 2 points. And I'm gonna make those points exactly be the bisector of my circle. So I'm going to massage their x, y, and z coordinates. I'm going to hit apply. That now becomes a perfect bisector. I'm going to choose both objects. I'm going to go to my trim modifier. I'm going to remove the outer pieces. I'm going to remove the bottom piece. And lo and behold, there is my hemicircle. Now, if I click on this object, notice that its pivot point, or its centroid, or what I come to call the gizmo, is not living at a point which is convenient to me if I want to put this guy upright. So what we can do to relocate that pivot point is right-click, and we're going to do select vertex rather than object. And now I can choose a vertex, one at the base of the hemisphere. I'm going to hit enter. And if I now go back to select object, notice that my gizmo or pivot point has now been relocated to the vertex that I chose, which also means that if I now were to rotate this and roll it upright, that now we have rotated that hemisphere around that new point. And from here on, it's rinse and repeat. I'm going to choose my hemisphere. I'm going to do an extrusion, 180 degrees around its base. I'm going to hit apply, and there you have your hemisphere. And from here on, it is a matter of choosing the faces that you want to predict on. So there you have your first introduction to how to use these tools and the modifiers to come up with rather complex shapes within a matter of seconds. Any questions at this point?
There was one that I got messaged from Jane about importing DXFs. So I'm putting a link in the chat to the MAPP 3D help website. Merlin will talk about this, but we have a whole section on importing drawings. Important to note for DXFs, you want to be saving as a 2013 file. And then for SketchUp files, you want to use SketchUp version files from 2015. Those are generally the two biggest issues we see. And back to you, sir.
Here, we're going to look at some Boolean operations, just to give you an impression of what they do. So basically, this to me resembles a nut and a bolt. Long story short, we have a cylinder, and that cylinder intersects a cube. And what I can do when I select both of them, select the cube and the cylinder, I can go to my modifiers and I can do union, intersect, or subtract. What happens if I do union? I select two objects to perform the union. I'm pretty sure that I did that. Let's select them once more and let's do the union. And what that does is that it unites my two three-dimensional solids and makes them a single three-dimensional shape. So the word union literally does what it suggests, which is that it unites two three-dimensional shapes. So let's undo that and let's look at a different Boolean operator. We're going to start with our primitives once more. I'm just activating them for prediction so that they get a shade for you to see. What happens if we do intersect? Well, if we intersect these two, then we're going to see the volume that they have in common. So let's select both of them. Let's hit intersect. And what we're going to see is the volume that is mutual to both of the primitives, which is, of course, the height of the rectangle and the cylinder with its inherent diameter. That is what intersect does. And finally, there's a third option that we can use, which is, let's activate these guys once more to give them mass, so to speak. There is the subtract. Now, what subtract requires you to do is literally subtract one volume of the other. So if I now were to select the cube, then it's going to remove its volume from the cylinder, and what is left over is a cylinder which basically now exists of two pieces. Whereas if we subtract the other from the one, then it should not come as a surprise that we'll end up having a hole in our cube. So let's select those two guys once more. Let's do subtract, but this time we're going to subtract the cylinder from the rectangle. And lo and behold, now we have a cube with a hole in the middle. Suffices to say that with these modifiers, which admittedly seem somewhat abstract, you can do rather complex shapes. And to give you an impression, I'm going to start a new project. Oops, I'm already to the limit. So I need to close a project. Let's see if I have another one. Let's use this guy, because there's also the snapping tool, which I wanted to discuss. So notice that the imported DXF file over here has more structure. Layers are in there. It's already been layered in AutoCAD, and that allows us to remove some of the elements that do not serve our purpose at this point. Here we see that same shell theater as before, except with additional layers. I don't want to see the plans. I don't want to see the shell. I don't want to see the stage. I don't want to see the structure. I have no interest in trees or grass. Basically, at this point, I only want to keep the the amphitheater. And I'm also going to hide the layer for now, which contains the Lena system. So what else can we do in order to make use of the imported DXFs? Well, notice that if I right-click somewhere within my model view, there is the select snapping tool, which I can activate. And what that does is when I choose my free draw tool, it will automatically snap to any of the vertices in the imported drawing that I had. So why don't I start somewhere over here by zooming in using my scroll wheel on the mouse and see what I can start drawing by snapping to this point. And I'm going to draw what we've come to call at Meyer Sound an audience profile. So the next thing that I want to do is I want to snap to this point. Okay. Oops. Let's capture it. Okay. Let's try that again. You can do it. Okay. I ended up creating two, be it may. And the final thing that I want to do is I want to snap to that outer corner of the seating plane. And I'm going to snap to that one. Come on. I'm going to snap to that one. I'm going to hit enter. And there we go. Notice that it's highlighted in yellow. It's yellow and yellow, which is a poor choice. But if we go to multiple viewports, you can see that the line segment that I drew is completely flush with the side of the audience. Also in front view, that we see that it tracks the elevation of the audience. It gives me a nice audience profile, as we've come to call this. And what I can now do is I'm going to take note of that first point where my gizmo lives, which has an X and a Y value of 702 and 0. Because now I can do another extrusion, an angular extrusion that is, of 180 degrees around the XY coordinates of that first vertex. And if I do that, apply, then lo and behold, within a matter of seconds, I now have an audience plane that nicely tracks the geometry of my imported SketchUp drawing. So that's where your snapping tool, comes into the equation. And while we're here, we might as well make use of the cookie cutter approach at this point. So imagine for a second that for all we know, there's an aisle on either side of the center that basically divides this audience in three pieces. Well, I'm surely have access to a plan view. So what I'm going to do is I'm going to draw a wedge in plan view, a wedge that outlines the aisle where I anticipate the aisle to run, consisting maybe 4 points. I'm going to hit C for close, and I'm going to give this volume. I'm going to give this mass because this is a two-dimensional shape, but using the same extrusion option, I'm going to give this, 15 meters. And notice that this is now basically become a wedge shape with volume, with mass. And what I can now do is I'm going to offset this a little bit down ever so gently. And what I now can do is I can select both volumes and subtract one from the other using the same Boolean operators that we saw before. So I'm going to do subtract. Okay, it wants me to select two shapes. Well, I'm going to select two shapes. I'm going to do subtract. And I'm going to subtract the wedge that I created from the audience plane that I had before. And notice that I'm now left over with two shapes without the wedge that I just subtracted. And then I could rinse and repeat and do so on the other side as well. And that allows you to come up again with some rather complex shapes within a matter of seconds, using those Boolean operators, which we've come to call the cookie cutter.
And of course, you would then, if this were a seating plane, you would offset that prediction plane a little bit. Right. Alan was asking, would you raise that by 1 meter to represent the ear level?
Because that's a very good question. Obviously, at this point, that is where our feet touch the floor. I can go to any of those faces, note that they highlight, for all we know, the people in the stalls downstairs, which are phase 3 and phase 1. For all we know, they might be standing. So let's make that 6 feet, or in this case, meters. So let's make that 1.7. And let's make the other one, let's Let's make the other one 1.7 as well. I didn't want to rename it. That happened accidentally. But for all we know, the people in the section that is rising, that is elevated, they are seated, and in meters that would be 1.2 meters. And that means that I can give each of these faces, I can give these unique offsets to account for the listening height where our ears are. This could be stalls 1, this could be stalls number 2, and for all the, I know this might be raked, and this might be raked. But using those rather abstract Boolean operators, you can come up with complex shapes in a matter of minutes.
The cookie cutter method, guys, everyone is one of the most powerful tools, especially when dealing with complex geometry. Especially, we in theater, we have to deal with VOMs, we have to deal with aisles, and sometimes, balcony walls. So just drawing a shape, doing a basic angular extrusion like Merlijn is doing here, and just drawing another shape on top of it, extruding it up, and then subtracting allows you to cut out sections of your prediction plane to make it a lot easier for you. So it's a great tool, and you draw the shape that you want. It could be any shape, and using the snapping tool that Merlijn showed is also great to lock to the shape of whatever geometry you're working in. Then you extrude that shape that you draw and bring it down to where it's covering the whole entire surface that you're trying to cut out, and then click intersect, and or you can click subtract, and there you go.
So, this is really the way to come up with complex shapes very, very fast. So that is your first sample of how to add geometry. The next thing that I want to talk a little bit about is attenuation. How is SPL shown in these model views? So imagine that you have a perfectly omnidirectional sphere hovering over a two-dimensional shape. If we were to do a prediction, then we're going to get jet colors where red is loud as in hot and blue is cold as in soft. It should not come as a surprise that the loudest position is directly underneath the omnidirectional source where the distance is the least. And that, of course, constitutes the ceiling of my scale, which is set automatically. So the scale in attenuation mode always calibrates itself to the loudest point in the prediction. And then there is there comes a place where we see transition from blue to black, and that constitutes the floor of my scale. And that means that everything that's rendered in black is 12 dB or more below the ceiling of my scale. The difference between these extremes, that is what we call the range, and that is a user-definable setting. Currently, the range is 12 decibels, but that range could also be 42 decibels. Long story short, in attenuation mode, the scale always automatically calibrates itself to the loudest position in a prediction, and then the floor will live at whatever value you set your range to. It will live below that. And with that, we can go to the topic of, is there a way how I can tweak my SPL settings to do a quick design? And that will be the next topic that I wanted to discuss. I have a project ready for this. It also means that I need to close a project because I can only work with 5 open projects at once. So I already have that in the list here, and that should be the pass fill. So over here we have a very simple approach. We have an audience plane, we have a stage, we have a bunch of front fills, and we have 2 point source loudspeakers up in the air. Now, let me make sure that my SPL settings, by right-clicking somewhere in the model space, that my SPL settings are set to the default for attenuation, which is a range of 42 dB in full resolution. We'll revisit this later. If I hit apply OK and just choose one of my loudspeakers, let's choose house left and do a prediction, then we're going to see the propagation of SPL in the activated listening plane. And the top of the scale, which reads 0, will be determined by the loudest position with respect to this prediction, which is somewhere here where this loudspeaker touches down at ear height. And then the range is 42 dB. And that means by the time we would see black colors, you would be down a level by 42 dB or more. Now, there are several things that we can do at this point. This is a beautiful continuous scale with no discrete steps. Looks pretty, but more often than not, we would like to have discrete steps, maybe every 3 dB, a color division. And what that basically gets us, without having to recalculate, is it gets us a terrain map, like an elevation map that you can look up on the internet. And what you see are so-called contours. And what those contours imply for a terrain map is that if you were to wander along those contours, your altitude doesn't drop and your altitude doesn't go up. So in terms of loudness, whenever you walk these contours, you're listening to the same level. Whereas if you now come towards the base of the loudspeakers, you start to see redder colors, hotter colors, and that means you're going up the mountain, your elevation is rising, your level is rising. Whereas if you go in the opposite direction, you're descending the gradient, you go down the mountain, your level is dropping, and every color division would be a 3 dB drop in altitude, if you will. And what we can do is we can massage these values even further, and we can say, you know what, I only want to have a range of 12 dB rather than 42, and I only want a color change every 6 dB. And if I do this, then it only needs to re-render, it doesn't need to recalculate. And now we only have 2 shades of color. We have red and blue. By the time I see black, I can infer that my level has dropped by 12 dB or more. And since we typically try to achieve 6 dB of uniformity, that is to say everyone within 6 dB of level variance, I can now quickly see that everybody that is in the sole custody of house left within that red area is experiencing level variance of 6 dB or less for the frequency range of interest. I could also select the front fill and repeat the process. If I now select that front fill, then we're going to see a prediction for that front fill exclusively. And since we set our scale to only show 2 shades, that is to say red and blue, we can see the people that are in the custody of that front fill within 6 dB of variance or less. By the time we see a contour and we see a change to blue, it means that the level has dropped in excess of 6 dB, and that is about the time that the other front fill needs to take over, such that its red color kisses the color of the other guy at the midpoint in between them, so that in unity, if I select the 2 of them, that they extend the line, such as uncoupled line sources are known to do. And now I see that in a team effort, we have both of these loudspeakers taking care of the first 2 rows or so within 6 dB or variance or not. So that is what we do for a quick pass fill approach. I will now do the entire system, that is to say all 6 front fills as well as the 2 point sources, and everyone better shows up in a red color. That is to say the majority of the audience better shows up in a red color, telling us in a blink of an eye that everybody within this red region is within 6 dB or variance or less. And if I were to expand this design, I probably need an outfill over here and an outfill over there, but we'll save that for another day. So that's how you can tweak those SPL settings to meet your goals and to come up with designs very quickly. In 2 weeks from now, we're going to see Bob McCarthy do Space Map Go room design, and that will involve a lot of examples where we only see shades of red and blue, basically a pass fill mechanism in the interest of quickly finding out who is in and who is out. I want to talk a little bit about prediction speed. In the interest of managing expectations, this is what you need to know about MAPP 3D. The prediction speed, or the time that you have to wait, is proportional to the mesh density. And that means that every surface, every plane that you activated for prediction is chopped up into little triangles. And the vertices where the triangles meet at the nodes, that is where SPL is calculated. And that means that the higher the density, the meshing density of a particular face is, a particular surface is, that it should not come as a surprise that the prediction speed goes up proportional. That being said, you have 5 resolutions to choose from, ranging from very low to very high, and this is how you can manage speed versus accuracy. That being said, I can work at low resolution to get a first impression of, am I aiming the loudspeaker in the right direction? And then if I want to see the interaction between adjacent loudspeakers or arrays, I want more granularity, I can ramp up the mesh density to match my workflow. The other thing that you need to know is that the prediction speed is also proportional to the number of, mind you, both visible as well as activated faces. That is to say, activated for prediction. You can have a gazillion faces visible within your model, but if only one of them is activated for prediction, then you're still going to have a very speedy calculation. What we tend to do for larger rooms is that we prepare our listening planes in such a way that if we're dealing with symmetry, that we can only work on half of the room, and then we mirror everything upon conclusion and complete the room. So by working with only half of the room, you greatly reduce the number of activated faces. You can also divide and conquer in such a way that you make a dedicated listening planes for the people that are in the custody of the front fills and a dedicated listening plane for the people that are in the custody of the under balconies, such that when you want to predict those, that you only activate their intended target designated areas rather than having to look at a prediction for under balconies with all faces activating, including the ones that house audience members that are not in the custody of those under balconies. So surely that is pretty self-explanatory. Also important to point out that the larger the area is, the more triangles it will consist of, depending on the mesh density that I'm working at. So again, if you have a large area which is the size of a football field rather than an area which is the size of a stamp, then it should not come as a surprise that the larger the area, the longer it will take for that prediction to take place. So one of the things that we do for large-scale events in the interest of setting our splays for our curvilinear line array elements is, why look at an entire audience plane when you can also just look at a strip in the interest of setting your splays? And I think that merits a brief demonstration. So here we have 12 Leo elements that are covering a plane the size of a soccer field. And needless to say that if you were to mesh this, that is a lot of nodes, a lot of number crunching. I'm not going to take you through the entire prediction, but if I hit predict while activating the entire surface, this is going to take about 2 minutes at middle resolution. Predicting the entire map doesn't give me any additional information in terms of revealing new information in the interest of setting my splays. So I'm going to cancel this, and instead of doing the entire audience, I'm just going to take a very thin strip, which is about 6 feet wide. Suffice to say that the area of that strip is, of course, significantly smaller. And if I now were to do a prediction, this will take significantly less time. It's not going to take 2 minutes. As you can see, this took about 20 seconds. Why? Because this area is significantly smaller than the entire plane, and it still allows me to set my splays and get an impression of the SPL distribution front to back. And when I'm happy with my splays, then I can go away from the strip, and now I can do, the entire plane. But all of this to keep the workflow expedient. And with that, we've covered most of the features, and I think now the time has come to look at the integration with Compass and Compass Go. Here we have MAPP 3D in the left. We have the mature Compass control software, the full version. I'm using a virtual galaxy, but it doesn't defy the demonstration. I've called it My Galaxy. It lives in its own tab. This is familiar to those that work with Compass. And at the same time, I'm using Reflector over here when I'm going to start Compass Go. And if I start Compass Go will tell us, hey, I found a galaxy on the network. So I'm going to say, great, please connect to the galaxy on the network. We have a dedicated SpaceMap Go webinar that I highly encourage you to watch.
Compass Go webinar, right?
Sorry, there we go. That we would. I jinxed it when I said, correct me whenever I say SpaceMap Go, because then I mean Compass Go. So I made everything equal. We're looking at output 1 of the galaxy. We're looking at output 1 on Compass Go. And now I'm going to go to my virtual galaxy in the MAPP project, and I'm going to do something extremely ill-advised. I hope that none of you do this in the field, but I'm just going to do something completely random with a Q in output channel 3. And, this EQ requires parental supervision and contains explicit lyrics. So please don't do this in the wild. But this is just, while we're at it, why don't we throw a couple of all-pass filters at it? So I'm doing something extremely ill-advised. And for good measure, let's do a high-pass filter somewhere over here. Something extremely ill-advised in channel 3. And let's go to channel 3 in the Compass Go as well. And let's go to channel 3 in the mature version of Compass. And now I want to push this to the Galaxy devices on the network. So I go to my tools, I go to my signal processor management, and notice that Galaxy number 1 over here is the Galaxy, the virtual Galaxy in the MAPP project. But now I'm going to click Select Discovered Device, and that will bring up a dialog, and it says MAPP 3D found a Galaxy on the network. I'm going to choose that, and now I have the option to either push the settings in MAPP 3D onto the Galaxy on the network, or the other way around, I can pull the settings on the Galaxy, the real one on the network, and pull those settings into the MAPP 3D project. In this case, I'm going to do the push, I'm going to do connect, and notice that within a matter of seconds, my very ill-advised EQ that I made in MAPP 3D now shows up in near real time on both the mature version of Compass as well as the mobile version of Compass known as Compass Go. So let's close this dialog. And notice that from this moment forward, they're linked. They're in complete synchronicity. They're joined at the hip. And that means that if I were to go to MAPP and change the corner frequency of this high pass filter, that both the Compass Go as well as the Compass reflect that change in real time. I can also do it the other way around. I can change the high pass frequency in the mature version of Compass Go, and now MAPP 3D tracks in real time as well as Compass Go. And suffices to say that if I were to go and use the index finger and change that high pass frequency on my iPad, that everybody tracks in real time. And that is great because that means that depending on your personal preference, you could do all of your processing in the virtual Galaxy or Callisto or Galileo within the MAPP project and push those onto the network. Or if you rather work in Compass because it's within your comfort zone, they're now joined at the hip. And if these happens to be 16 Lion elements that require delay integration, I can do OK and notice that within seconds, this is going to turn up blue, showing us that that the settings have been adopted by MAPP 3D. So, or you do it in Compass Go, and that means that while I'm on the bus, don't have to be online, I can already do a big part of my calibration within my MAPP 3D project, and then when I get on site, I can push it onto the network, onto the Galaxy devices in the system. Then I can start doing my calibration process as you're used to do. And then you could move over to Compass Go and start walking the room with the iPad while you're voicing the system subjectively and doing your seasoning to taste. And the even more interesting aspect of this is that as long as MAPP 3D is running, it will archive all of your work because it tracks whatever you're doing on the iPad or on the Compass software. It tracks all of that, and that means that by the time you're done, you could store it as a separate file, and it will have all the changes that you made during the course of calibration with respect to the file that you pushed onto the network when you came off the bus and arrived on site. And that means that you can also use MAPP 3D as an archival tool. Maybe, despite your best efforts, there was this certain I don't know what that didn't meet your expectations, but time didn't allow you to figure it out on site because right, it's showtime. And then on the bus to the next stop, you could then recall that MAPP project, which would then have all the changes that you made during showtime, and you could start to investigate why things did not work exactly the way you anticipated to it, and be better prepared for tomorrow's show. So that's something that we take great pride in, the interconnectivity between these three pieces of software in real time. And that brings us almost to a close. Now that we've talked all about that, we can finish the official part of the presentation. We looked at the integration. So where do I download the application now that I have a first impression? You go to the Meyer Sound website and you go to products. And depending on the day of the week, MAPP 3D, for all we know, might show up in the feature products. If not, you need to scroll down the list until you see the row that has MAPP 3D. You click on MAPP 3D, which will take you to the product page, and the product page consists of several tabs, and from there you go to the register tab. Now, depending on what you're doing, you need credentials to log into the website. However, those credentials are not the same credentials as the ones that you need for registering to MAPP 3D. So do not mistake the credentials that you need to log in to the website for the credentials that you need to make use of MAPP 3D. Assuming that you successfully register, you're going to get an email that confirms your registration and requires you to activate your registration. Assuming that you've done all of that successfully, you're going to go to the fourth tab, which is your account. You're going to log in using your credentials, and that will take you to my MAPP 3D account, which is a 3-tab window, and the middle one has my software, and that is where you can download the latest version for Windows or for Mac. So with the minor caveat of the login credentials, this is a very straightforward process. And then what about additional help? Well, as Josh already pointed out, there is a very elaborate verbose website with many examples and best practices, which can be reached by either visiting map3dhelp.meyersound.com or by simply clicking on help within the application from within the main menu bar. That is really the first line of defense that we encourage you to go. As I said at the beginning of this session, we did several roundtables which talk at greater length about some of the highlights that we discussed here. So be sure to watch those if this has your interest. And so what about feature requests and bug reports? Well, if you have feature requests, if you would like to see something improved or further developed, we kindly ask you to go to the Meyer Sound contact form. If you go to the contact form, you will notice that there is a technical support section. Technical support section. And there you can choose software support. And then you, of course, have to let us know that you're using MAPP 3D. And then does it involve a feature request or a bug report? And then we kindly ask you to include a brief title, description of the feature, and why the feature is valuable. A feature request could also include a request for a particular loudspeaker model. Maybe you're using a legacy product, which at the time is not present in MAPP 3D. Well, please let us know, because we have a rather large portfolio and the scanning process is an involved process. So in order for product management to prioritize certain speakers over others, we basically require majority vote for a certain make and model. And by submitting your feature request or loudspeaker model request, you can push certain models up the food chain and make it more likely that they will get prioritized. It could also be that you encounter a bug. Please include a brief title, the steps to reproduce the issue, your operating environment, your operating system, and any other relevant information that we need to replicate your findings and how it differs from the result that you were expecting to see. But I'm more than happy at this point to answer any questions you might have.
One thing that we didn't touch on in this, but I think is really cool and important, in theater especially, is, we don't have time in almost anything we do, and time is always a very valuable resource. And a cool feature about MAPP XT and now MAPP 3D is you can insert what are called virtual microphones, and you can actually move microphones around in the 3D space to see what the expected frequency response and phase response of your sound system is. You can also work, if your drawings are accurate, you could also timeline your system and do all sorts of really interesting things. And I call it doing my homework before I walk on site. And it's just a really fun tool. The other cool thing is I highly encourage you to just do that. Put a virtual microphone in before you walk into a space, measure the speaker, in Map 3D, and then put a real microphone when you walk into the actual space and see the difference in the trace. Now, obviously, coherence is a thing and reflections of a room, but it is incredibly accurate. And every time I do it, I'm always really amazed at what was predicted and expected to what it actually was on site.
You know, that is functionality that those that are familiar with MapXT have come to expect of us. So this no longer being 2D but 3D and offline. So again, you know, we had 4 roundtables that we needed to compress into a 1. So we focused on the features that are new, and we take pride in all the features that we preserved, including the microphones. And yes, do your homework, rough it in while on the bus, and then push it on the network. It will get you comfortably within the ballpark, and you know, you might find yourself shaving off a millisecond more or less, but you're going to get comfortably close. Yes.
Yeah. And next week, just I don't know if you have a slide, Merlijn, but next week we're going to talk about Roundtable 3, which will be theatrical workflow for Space Map Go. And we're going to start from the system design, and we're going to go all the way through to programming your show to opening night. And we're going to go through that process as an example. We might also, if I can get it working, we might have some audio examples as well, and all sorts of fun other things. And then we're bringing it all together with the system design aspect with Bob McCarthy on week 4.
Excellent. I do want to thank my co-host, Josh. Thank you for being here. Thank you, TSDCA, for the opportunity to allow us to talk about Map 3D. Looking forward to the next 2 sessions on behalf of Meyer Sound. Thank you very much. Please stay safe. Please stay healthy. Best to you and your loved ones. And we're looking forward to seeing you in 1 week from now. Bye-bye.
Yep. Thanks. Bye, everyone.